When looking at sequences and series, it's very important to understand notation. If I have a sequence of numbers, so just a list of A1, A2, A3, so on up through AN, and I want to add all of those terms together, we can write each of those terms out, or we can use what's called summation notation. With that summation notation, we have an index, which tells us which terms we're going from. In this case, we're going from the first term up to the nth term. And the Greek letter sigma is used to indicate that we're adding all of those terms together. We can adjust this to tell us how far we want to go up in terms. Maybe we only want to add the first 5 terms. Maybe we want to add from the 5th term to the 12th term. So we can adjust those, and then this is the generalized use of whatever that sequence is. So let's look at an example here. If we want to write these sums in expanded form, notice here that we are adding terms 1, 2, 3, and 4 of this sequence. And so what's happening is we're going to replace I each time with the next consecutive integer. I like to think of it as a ladder. I'm starting at 1 and I'm climbing up the ladder until I get to 4. So this becomes 3 times 1 minus 2 plus 3 times 2 minus 2 plus 3 times 3 minus 2 plus 3 times 4 minus 2. So we have gone from 1, 2, 3, 4. Everything else stays the same. And those terms become 1 plus 4 plus 7 plus 10, which is 22. Following that same idea down here, notice we're not starting with 1, we're starting with 3. We're going to have 3 squared plus 4 squared plus 5 squared, climbing up that ladder to 9 plus 16 plus 25 equals 50. Remember that sigma notation is nothing more than just a simpler way to represent addition or the summation. And so the properties of addition still apply. Notice that we can rearrange the terms. So order doesn't matter. We can do the first sequence and then the second sequence. We can adjust those. We can also pull the constant out. If C is a constant, we can add up all the terms first and then distribute that C across it. And likewise, if we want to split it up, we can go, instead of going, say, from 1 to 50 for our I value, we can go from 1 to 25 and then from 26 to 50 in terms of our values here for our indices. Do note that statements such as this that look similar are not true. So we cannot multiply 2 sequences together and then add them. We have to follow the proper notation there. There are a couple shortened summation formulas that are going to make your life a little bit easier, and I do encourage you to learn these. If we're trying to just sum the value of 1 n times, it just becomes n. We're not actually changing any values. We're just adding 1 plus 1 plus 1 n times. If we're adding up I from 1 to n, it's going to become n times n plus 1 over 2. We'll show the proof of that here shortly. The summation of I squared, here's a shortened formula for calculating the summation, and then I cubed is right here. If we look at the proof of this second term, so if we're looking at the summation of I, and we want to show that it's equal to n times n plus 1 over 2 when we're going from I equals 1 to n. Let's start off first of all by giving this a name. Let's call this S. So I can say that S is equal to the sum from I equals 1 to n of I, which is simply 1 plus 2 plus 3, and so on up to n. Remember, we're climbing up that ladder, so I'm adding 1 plus 2 plus 3, and so on all the way up to n. Notice this addition can be formed in any order. So I can rewrite this idea, and I can say that S is also n plus, notice the term right before here is going to be n minus 1. The term right before that would be n minus 2, and so on. And then I can add plus 3, plus 2, plus 1. So all I've done is switch the order here. So if I add my pink S, 1 plus 2 plus 3 plus all the way out to n, and then I add that to my purple equation, n plus n minus 1, so on. Notice I get 2s equals, this gives me n plus 1. These two terms are also going to give me n plus 1, and so on all the way down to here, n plus 1. And that's going to occur n times. So I end up with 2s equals n times n plus 1. And so if I divide by 2, that's where we get the s is n times n plus 1 over 2. Let's use some of these properties that we've just looked at to practice evaluating sums. So for example, here in choice A, notice we can split these two based on the properties of addition. So I can rewrite this as the sum of I equals 1 to 9 of 7i minus the sum from I equals 1 to 9 of 3. Because that 7 is a constant, I can pull that out and I get 7 times the sum of I minus 3 times the sum of 1. Again, I'm pulling out that 3. And then following those rules that we just looked at, we know that the sum of I becomes that n, which is 9 times n plus 1, which is 10 over 2. And that's coming from our summation formulas that we just looked at. And then minus 3 times n, which in this case is 9, again from our summation formulas. And this results in 315 minus 27, which is 288. Applying those same properties here, again, I can pull out my constant of 3. I'm going from I equals 4, in this case, to 6 of I squared. Using the formulas that we looked at of the I squared, this becomes 3 square root of I equals 1 to 6, because we know that that formula applies from the value of 1. I squared minus 3 times the square root from I equals 3. I equals 1 to 3. So we're going back so that we're just covering from 4 to 6. And using those formulas, we then get 3 times that n times n plus 1 times n plus 2. So we get 6 times 7 times 13 over 6 minus 3 times, again, n times n plus 1 times 2n plus 1 over 6, which results in 273 minus 42, which is 231.